So I'm here with Taylor Lloyd. Taylor is a former student from the University of Alberta, although he has never taken 415. Uh, but he did work with the compiler for Gazprea nonetheless. So Taylor, can you start by telling us how that happened?
That happened because I ended up getting a NSERC position in my second year of my computing science degree, and I ended up creating new labs for 229. So if anyone has taken 229 and done some of the original ARM labs, you can blame me for that. Uh, but after that, I just remained really interested in microarchitecture and compilers. And so I was out on a different internship when Nelson sends me an email and says, there's this very cool opportunity happening in Toronto. Uh, the Hardware Acceleration Lab at IBM is building this new programming language, and you should help them out, or you should be a part of it. And I said yes. And that's how I got a co-op position at IBM.
Yeah, I remember you were at Amazon at the time, and I said as soon as you finish your Amazon assignment, you should move over to IBM and work there. So there, when you got there, Gazprea, which at the time was called Dash, was being started. Bob Lane had spent the New Year's holiday designing the language and doing the rudiments for a compiler. And then there was a small team that was working on that. And if I recall, what happened is that after a few months that you're there, there was this extreme blue experiment that happened. That is, you got a number of other people that came in, not as compiler developers, but as users of the language trying to figure out to put a business case together for that. So tell us a little bit about this experience of trying to build the first compiler for this language and supporting these people.
Yeah, so IBM's Extreme Blue program is a 4-month intensive internship where they put together these teams of, I think, 4 or 5 interns. And they're assigned to various business units throughout IBM globally and asked to make a business case for a new push to try and get investment and bring up new good ideas to IBM's leadership. And so we got one of these teams, and with our hilariously unready compiler, we asked them to build a case for using, I don't remember if it was Dash or High at the time. We were very ambivalent on what we were going to name everything. But we asked them to build financial models using our new compiler, and then doing it traditionally like a mathematician designing models would in MATLAB, and then also like a accelerator programmer would. So in both single-threaded C++ and then also a C++ and GPU-enabled version. And the goal was to show that you could write code that is very understandable to mathematicians who don't really understand architecture, but do understand mathematical concepts, matrices, arrays, and how to manipulate them, and yet still achieve performance competitive with C++ and even offloaded GPU code. Um, and we had some really impressive results there, actually. After lots of bug fixing and working with this team to get everything working, we were able to show for, I believe we ended up doing some sort of complicated Asian derivative scheme. We were able to show performance comparable to if it was hand-tuned.
Yes, Gazprea was, the motivation was, as Bob said in my chat with him, the computational finance realm, right? It was how we can use all these different accelerators that at the time were relatively new, um, to do acceleration of this kind of applications that were at the time all programming in MATLAB, and we know that lots of Python is still in use for that. And so one of the questions was, with a better language, could you do a better job? I believe that the language is good, that the language is a good fit for the problem, but the language did not make out of the door.
It didn't. I agree. The language designed was really solid. It had a lot of very convenient high-level concepts, but with strong static typing. This meant we could do things like have first-class matrices and arrays and do operations on them easily. And in fact, we had a very complicated system behind the scenes where we had this massive runtime library that could express these matrices in a whole bunch of different ways. So we could play tricks with memory layouts and offload them efficiently and coalesce memory and do all the things you need to do to make a GPU relatively efficient. But a big problem we ran into is writing a compiler that can turn correct language code into a running executable is really only the first step of the problem.
Yeah.
Because what really matters is what you do with incorrect code. And we didn't have the time to develop clean error messages. We didn't have time to figure out how to offer things like fix-me's. And we did run headlong into the issue that very few people want to learn a new programming language. They're quite happy with the ones they already have.
And I mentioned to the students what you're saying about what you do with wrong code and on with corner cases. That was one of the main selling points to Bob when I proposed that we could use it in 415 in our compiler course because of the competitive testing that we have in the course, where he saw the opportunity for getting lots of corner cases that would be talked up by students when they are trying to compete with each other to try to break each other's compilers, right? So that would be a great asset. But moving forward, remember that as soon as that project was over, as soon as it was clear that Gazprea or Dash or High or whatever it was called at the time wouldn't go out of the door, you quickly got yanked from that team and landed in a new team where great things happen, right? With the Summit Sierra efforts with IBM for building the fastest computers in the world at the time. And you end up doing a fairly significant contribution to the software stack there. Can you just talk very briefly about that?
Yeah, it ended up being this amazing opportunity because working on Gazprea, or again, whatever name it was a great way to learn about compiler development in theory with a very new project that used a bunch of modern utilities and was small and fresh and easily understood, which was great because that transition was a rough one right into IBM's XL compiler, which still has code that has copyrights of the 1970s in it. So it's definitely a huge monolithic beast, a very impressive compiler. It can do amazing things, but it's a big project. And I ended up working on the OpenMP offloading in that compiler. And so for Summit and Sierra, which were IBM and NVIDIA's supercomputer proposals to the DOE, they were pairing these beefy IBM Power 9 machines with, I believe, like 8 or 16 NVIDIA cards per node. And so a huge important feature for this delivery was any sort of scientific applications had to be easily offloaded onto these GPUs, which were contributing most of the compute power of the supercomputer. And yes, I helped implement the GPU offloading technology and analysis to refactor loops for GPU offloading and reorganize memory accesses and a whole bunch more.
Yes.
I got inserted right into that core compiler team.
And one interesting thing is that you worked together with Art and Chicken when you were there already, and then after you left, Art and continued the work. And so you miss being at supercomputing in Dallas, where Summit and Sierra were being revealed, and where it was very clear to IBM, to IBMers and to the competition that it was our collaboration that had made OpenMP as fast as it was when those supercomputers were revealed. And one of my favorite memories is to have one of my great colleagues come to me and say, "You beat us." and so that was a great memory from that event, and was thanks to the work that you and Arten is actually an alumni of 415. Um, and but then time moved on. You finish your degree, and you are now back in Seattle.
I am. I'm back at Amazon now. I'm working with Amazon Robotics and actually applying all my knowledge in totally different ways. I'm now working on embedded devices. And so we're building what is essentially a glorified Pixel 3 with a power connection to do advanced image processing in Amazon's warehouses. And so all of that work I did understanding how to optimize these complex systems, I now don't have to do the analysis part. I can just jump straight to the optimizations, which is a fun new way to apply it.
Yeah, so this highlights one of the things in my chat with Bob, that learning to build a complex software system, what you're gaining are skills, right? And one of the things that Bob emphasized, and we are emphasizing in this term, is the social aspects of building complex software. Not only the algorithms and how you write code, but how you interact with other people that are also writing code and contributing to the same infrastructure.
Mm-hmm. Yeah, the internships in general were hugely important for understanding how to use source control effectively, how to maintain software for longer than, say, about a school term. But yeah, working with professionals and getting that early exposure in deeply technical systems really does help, because it teaches you how to structure your code so that others can read it, but also so that you can read it 4 to 6 months later.
Exactly.
Yeah,
Okay.
no.
So any final talks that you may have for the people that this week just started 415 and are facing, which is a very challenging project?
Yeah, honestly, looping back to that source control, it matters so much more than you'll think it does. Start early, learn to use and love Git. It has a steep learning curve, but you will really appreciate having spent that time, both in this course where it will save you from late nights where you're trying to get all of your code together and compiling, but also moving forward when you're finished school. Spend a lot of time figuring that part out.
Okay, thank you very much, Taylor.
Thank you, Nelson.